Hi everyone, you are welcome to DML Physics Concepts. Today we'll be looking at another topic which I titled Scalar and Vector Quantity. Kindly subscribe to this YouTube channel. Make sure you like this video and share this video to your friend. And at the same time, you turn on the notification bell so that once I upload a new video, you will be notified of those videos. Now today we want to look at scalar and vector. In previous classes before now, we've learned about what we call fundamental quantity and derived quantity, where we established that fundamental quantities, they are the basic quantities of measurement, and we said derived quantities, they are formed from fundamental quantities. So now we want to look at another categories or another type of quantities that we use in physics. Now we say scalar and vector. So what are scalar quantity? Now, scalar quantity is the one which has only magnitude but no direction. These are examples of quantity that they have size, they have magnitude in terms of their size, but they don't have direction. Now, examples of this quantity, we have density, mass, volume, speed, distance, time, energy, and temperature. So let's write something. So as we have it on the board, you can see that scalar quantities has magnitude but no direction, and these are the examples as we have it on the board. And what are vector quantities? Vector quantities, on the other hand, are the quantities that have both magnitude and direction. They have size, they have direction. So let's look at the examples. Let me give you an examples of let me give you an example so that you'll be able to get what we are talking about. Now let's say I want to say time, for instance. Time is an example of a scalar quantity because time only have magnitude, it only have values. For instance, I can ask you what is the time, and you say the time is 10:00 a.m. So the 10:00 a.m. is just giving us the magnitude of time. But if I say what is the direction of time, then you agree with me that time does not have a direction. That is a particular direction of time. No, time only have magnitude. So that's what we are talking about. So every quantity that has magnitude but no direction, they are referred to as scalar quantity. Now let's look at vector quantity. If I look at force, let me give you force. If I say 5 Newton, if I say force is 5 Newton. Now the Newton, the 5 is giving us the magnitude of the force. The force could be 5, it could be 10, depending on the size or the magnitude. So, but another thing about force is that force have direction, because force could be pulling. I can decide to pull this block towards this direction, and I can decide and call this one F1, and I can decide to pull it in the opposite direction, F2. So force will always have a direction at which they are acting. So in other words, any quantity that has direction and magnitude, they are referred to as vector quantity. So let's look at something else now. So let's look at vector representation. How do we represent vectors? Vectors can simply be represented by a line showing its magnitude, an arrow end showing its direction. For instance, if an object moves northeast, this is the cardinal point. So this is the north, this is the south, this is the west, and this is the east. So if an object moves, or 5 Newton moves northeast, so I can decide to draw in this direction and call this one 5 Newton. So this direction is telling us how the object moves, which is northeast, but the magnitude is still 5 Newton. So we can use an arrow, a line, to indicate the magnitude, and we use the arrow end to indicate the direction. So a force can move in this direction, and we call the magnitude 10 Newton. That is if it moves towards the east. So the magnitude is represented by the line, and the arrow end indicates the direction. So that's how we represent a vector quantity. Most of the time, we always write, for instance, if I want to write force, I want to represent it as a vector quantity, I put an arrow at the point. The arrow I'm putting at the point is to tell me that it's a vector quantity. If I write velocity and I put an arrow at the top, what I'm telling us is that this velocity is a vector quantity. So this arrow, the line and the arrow, indicates that the quantity I'm talking about is a vector quantity. So next thing is we want to look at addition of vector quantities. Now if you have different vectors acting together, then how do we add vector quantities? So when we add vector quantities, the result we get by adding vector quantities is called the resultant vector. In other words, we can define resultant vector as that single vector which has the same effect in magnitude and direction as the original vectors acting together. So when other vectors are acting together, that single vectors which has the same effect in magnitude and direction as that original vectors acting together, there is regarded as vector resultant vector. So that's about that one. So resultant vector is that single vector as we have it on the board, so you can copy that note. Now let's look at how to add vector. Now to add vectors, there are about 4 ways or 3 or 4 ways we use to add vector. So depending on the direction of the vectors, we determine how we are going to add vectors. Let's look at case 1. The first case is that when the vectors act in the same direction, like we have it like this. All right, let's look at this illustration. Let's say we have a block like this, and then we have vectors acting in the same direction. So let's regard the vector as force. Let's say it's a force. You know, we said force is an example of a vector quantity. So let's represent this one as the force F1. This is F1. And let's say we have another force, also another vector, will be greater than F1, acting in the same direction, that is F2. Now, in this case, what's going to be the resultant force or the resultant vector acting on this block? So the resultant vector or force acting on this block is going to be the addition of F1 and F2. So in this case, the resultant of these two is going to be the resultant force or the resultant vector is going to be F1 plus F2. So what I'm saying in essence is that if for instance, if F1 is 2 Newton and F2 is 3 Newton, so what's going to be the resultant force on this block? So the resultant force on this block is going to be 2 plus 3. So it's going to be 5 Newton. In which direction? Along this direction, that is towards this direction. So that's why we are saying that vector quantity, we always have the magnitude and we also have the direction at which it's acting. So the overall direction is going to be towards the east. So the direction is eastward. In eastward direction, this towards the east direction. So let's look at case 2 now. So let's look at this case, vectors acting in opposite direction. So let's say we have another block, and in this case, let's say we have a force here, let's say F1 here, and then we have another force, let's call this one F2. If you look at this one, these two forces, they are acting on this block in opposite direction. So what's going to be the resultant force on this block, and what is going to be the overall direction moved by this block? So in this case, our resultant force is going to be F2 minus F1. It can also be F1 minus F2. The point is just you remove the smaller value from the greater value. So let's say this one is taken as 3 Newton, and let's say this one is taken as 5 Newton. So I ask us what is going to be the resultant force or resultant vector on this block. Since the forces are moving in opposite direction, we have this formula. Our resultant vector is going to be 5 minus 3. And what's going to be 5 minus 3 is going to give us 2 Newton. So the overall or resulting vector or force acting on this block is 2 Newton. So in which direction? If you look at this one is greater than this. Automatically, eventually, the object is going to move in this direction. So it's going to move westward. It's going to move westward. So you have to get that concept. So it depends on the direction of the vectors that will determine how we are going to add it, either by using the addition of F1 plus F2, or we are going to use F2 minus F1. Let's look at another case, which is case 3. So let's look at this case 3 now. When vectors are acting at 90 degrees to each other. So let's say we have this first vector, this vector 1, and then we have the second vector, let's say vector 2, this vector 2, and they're acting on this object. So this one is pulling the object in this direction, while this one is pulling the object in this direction. So they are moving, the force is acting on this body, but at 90 degrees to each other. So let's say this is the 90 degree. So let's assume that this one is let's say this one is F1, and let's call this one F2. So how are we going to find the resultant in this case? So to find resultant in this case, we are not going to say A plus B, F1 plus F2, or say F2 minus F2. So what we're going to do is like we are going to find resultant of this place by drawing an adjacent line, a diagonal. We draw a diagonal of this at the point of intersection between this point. So let's draw a diagonal. So what we're going to do is that let's close this one to make it a square. Let's square this up so that we'll be able to draw a diagonal. So draw a diagonal. So this diagonal, the value of this diagonal is going to represent our resultant in magnitude and direction. So let's take this one out. So if you take it out, it's going to look like this. So if it look like this, so it means, so this is where the object is acting. So this is our F2 acting in this direction, and this is our F1 acting in this direction. So this one is going to be our resultant. So if an object is acting at 90 degrees together, you discover that this is 90 degrees. So what we are going to use there, we are going to use to find this hypotenuse, because it's an hypotenuse. So to find this hypotenuse, we are going to use our Pythagoras theorem. Our Pythagoras theorem, applying it here, Pythagoras theorem states that c squared equals to a squared plus b squared. So we want to apply that where c is the hypotenuse. So we say, so we are going to say r squared equals to f1 squared plus f2 squared. So let's make r the subject, which is our resultant. Our resultant is going to be the square root of f1 squared plus f2 squared. So that's going how we are going to find our resultant. So in this case, let's assume that okay, then how are we going to now find our direction? So to find our direction is going to be the angle between the resultant and the horizontal, because we are looking at the direction of the resultant force. So the direction of the resultant force is the angle between that resultant force and this is the horizontal level. This is the horizontal level. So let's call this place our alpha. So let's take our alpha to be the direction. So by the time we know this angle, we say our direction is this angle to the horizontal. So let's look at this. To find this alpha, since I have F1, I have F2, you discover that in a right angle triangle, this is the opposite, and this is going to be our adjacent, and this is going to be our hypotenuse. So to find our direction, we just say opposite and adjacent. That's going to be tan. So the tan alpha is opposite over adjacent. So what is the opposite now? You just say tan alpha is going to be our opposite. The opposite here is F1, and our adjacent here is F2. So to find our direction is alpha. The direction is this angle. So our direction is going to be alpha. Alpha now is going to be tan inverse, the tan inverse of F1 over F2. So to find our direction, this one will be in degree. So our alpha in degree is going to be tan alpha, tan inverse of F1 over F2. So whatever this one gives you in degree is going to be the direction of this resultant force. So let's now apply it to this concept. Now let's assume that F is 3 Newton, and let's take F2 to be 4 Newton. So if I want to solve this one now, so we can say our resultant now is going to be the square root of, remember, F1 square plus F2 square. And what is F1 square? That is 3 square plus 4 square. So what am I going to have? R is going to be the square root of 9 plus 16. So R is going to be the square root of 25, which is going to be 5 Newton. So that's going to be our magnitude. So if this is our magnitude, then how do we get our direction? Since I say our direction is alpha degree is going to be tan inverse of F1 over F2. So what's our F1? 3 over 5. 3 over 4. So what's going to be our alpha now? So let me do it somewhere at this side so you can see the board clearly. So our alpha in the degree now is going to be tan inverse of what is going to be 3 over 4. So 3 over 4 is 0.75. That is 0.75. So our alpha in degree is going to be what is inverse of tan inverse of 0.75. It's going to give us 36.8. Let me approximate it as 6.87 and degree. So this is going to be our direction. So in this case, if I say what is the magnitude of two forces acting, force of 3 Newton and 4 Newton acting at 90 degrees to each other. Then the magnitude is 5 Newton, while the direction is 36.87 degree towards the horizontal. So this angle, how far here, is 36.87 degree. So that is how we find vectors acting at 90 degree. That's how we had vectors that are acting at 90 degree to each other. Now let's look at another case now. So now we want to look at the next case, which is vectors acting at angle theta to each other. Now the angle theta here is not 90 degrees, so the angle theta could be less than 90 degree or greater than 90 degree. When the angle theta is 90 degree, then we solve it as we resolve in case 3, whereby we use Pythagoras theorem. But now when the theta is less than 90 degree or greater than 90 degree, how do we resolve this component? So we resolve this vector by using what we call the parallelogram law of vector. So let's state parallelogram law of vector. Now let's state the parallelogram law of vector. It may look long, but it's just a concept that you need to understand. It's not just memorizing the law, but you should understand that this law is a concept itself. Now it states that if two vectors are represented in magnitude and direction by the adjacent sides of a parallelogram, the resultant is represented in magnitude and direction by the diagonal of the parallelogram drawn from the point of intersection of the vectors. Alright, let's look at the applications of this parallelogram law of vector. Let's say, for instance, we have two vectors that are acting at angle theta to each other. So let's say we have these two vectors. So let's say this is the vector, the first vector, this is the second vector, and this is the angle theta to each other. So they are acting as angle theta to each other. So let's call this one F1, and let me call this one F2. So that is what the first law states, when they are represented magnitude and direction by the adjacent side of a parallelogram. Now if you look at this, this is not yet a parallelogram. Now how do we make it a parallelogram? We make it a parallelogram by completing this shape. So I want to make it a parallelogram like this. So by doing this, I have made it to become a parallelogram. So if it's not a parallelogram, it means these two sides are parallel, these two sides are parallel. So in that case, if this one is parallel to this one, so this side is also F1. If this side is parallel to this one, it's also F2. So remember, so I made it a parallelogram now. It now said the resultant is represented in magnitude and direction by the diagonal. Which of the diagonal? The diagonal that is drawn from the point of intersection of the vectors. So remember, this is the vector F1, this is the vector F2. Where is the point of intersection? This is the point of intersection. This is the point where they come together, or the point they are coming from. So this point, we draw a diagonal of this parallelogram. So a diagonal is just a line that cuts the parallelogram into two equal halves. So we can draw a diagonal like this. We can also draw a diagonal like this. But the diagonal we are asked to draw, or the diagonal that represents our resultant, is the one from the point of intersection. Is the one from the point of intersection. So let me draw it up. So this is the diagonal. This diagonal is what represents our resultant force, or the resultant vector. So let's take this one out. If I take it out, it's going to look like this exactly. It's going to look like this exactly. So this is what we are going to have now. So we are going to have something like this, whereby this one is our F2, and this one is going to be our resultant, and this one is going to be our F1. Because if this side is parallel to this side, it's what we are going to have. But this is not our theta. Remember, the theta is the two together. The two together is what gives us our theta, not half of it. So what we are going to do here is to find our resultants. So to find our resultants, so we are going to do something. If everything here is theta, so remember this angle is corresponding to this angle. So if this angle is theta, then it means this angle is going to be 180 minus theta. Remember, angle on a straight line is 180. And if this angle, the whole angle here, every angle here corresponds to the angle here, that's corresponding angle. So definitely, then this remaining part here, which is this one, is going to be 180 minus theta. So this angle here is 180 minus theta. So that's the angle here. So if it is 180 minus theta, then how do we find R? Remember, to find R in this side, when the triangle we are dealing is not a right angle triangle, we find the side using cosine, the cosine formula. So what's our cosine formula? So our cosine formula is written as, so this is our formula. the resultant r equals to f1 square plus f2 square minus 2 f1 f2, that's the product of f1 f2, cos 180 minus theta. So to find the resultant in this case, this is going to be our formula. So you have to master this formula to find our resultant first. And how do we find our direction? Remember, our direction is always the angle between the resultant and the horizontal. Don't forget that your direction is always angle between the resultant force or resultant vector and the horizontal. So note that. So this is going to be our angle we are looking for. So to find this angle, then we are going to use what we call, this is the cosine rule, we are going to use sine rule. And what's the sine rule? Sine rule, you can just simply say sine is just going to be, let me write it like this, just f1, you can see f1 over sine theta, f1 over sine theta equals to r over sine 180 minus theta, and so on and so forth. So the relationship of this one is what we call sine rule. Sine rule is just talking about side over the sine of the angle or the corresponding angle to this side. So you just say f1 over sine theta equals to r over sine 180 minus theta to find our r. So by the time you write this, you just substitute these parameters into this and find your resultant in magnitude and also in direction. Let's look at an example to see the true picture of this application here. So let's look at this example. Let's say we have two vectors of 3 Newton and 4 Newton acting at 60 degrees to each other. So we want to find the resultant in magnitude and direction. So remember, what's going to be our formula to find magnitude resultant? First thing is you first draw the diagonal, and the diagonal is from the point of intersection of these two vectors according to the parallelogram law of so we have drawn the resultant vectors. Just complete it. Now after that, then we take this one out. So let's take it out for better understanding. That's why I like to take it out like that, so I'll be able to get the better understanding of it. So whereby this one is our r that we are looking for, this is our 4 Newton, and this is our 3 Newton, and this is the direction of our vector quantity. Alright, in this case, what we're going to do is we are going to use our formula. What's going to be the angle here? So if this one is 60 and this one is 60, remember angle here is 180 minus theta. So angle here is 180 minus theta. And what is our theta? Our theta is angle 60. So we can just rewrite this one and say 180 minus 60. And 180 minus 60 is going to give me 120. So let me just clean this off and just put 120 degrees straight up. Alright, let's now begin to apply the formula. So the formula is going to be now r square equals to f1 square, that is 4 square, plus 3 square, that is the second one square, minus 2ab, that is minus 2ab, and 2ab is 2f1, that is 3, then f2, that is 4, then cos 180 minus theta, and 180 minus theta is 120 degrees. So that's how we're going to find it in our r resultant now. So the resultant now is going to be, what is 4 square plus 4 square? That's going to be 16, right? That is 16 plus 16 plus 9, then minus 2 times 3, 12. 2 times 3, 2 times 3 is 6, 6 times 4, that's 24, minus 24 cos 120 degree. So it's got this one. Don't forget, the formula is very important. So let's write the formula again. R square equals to, let's call this adjacent square a square b square. So we can say a square plus b square minus 2ab cos 180 minus theta. Why do I use that formula? So whereby the a and b is going to be our f1 and f2. So you can just memorize this one or master this formula so that you can just use it straight off. So let's quickly do this now. Our r square is going to, what is 16? We have to have 25 minus 24 cos 120. And what is cos 120? And cos 120 is minus 0.5. So r square is going to 25 minus 24 multiplied by the cos 120 is minus 0.5. So our r square is going to be 25 the minus and minus is going to give you plus, that is plus, and this one is going to give you 12. So minus 27 plus like that. So the r square is going to give me what? It's going to be 37. The r square is going to give me 37. 37. And what's going to be the square root of 37? The square root 24 times 2, that is 12. Yes. So you're going to the square root of 37. And what's the square root of 37? The square root of 30. And the square root of 37 is approximately, let me just say 6.0828. So this is going to be in Newton, because we are dealing with Newton force. So I can approximate to, let me approximate to 2 decimal places. You can just say 6.008 Newton. So that's going to be our magnitude of the force. So let's look at the direction now. So for direction, don't forget that direction is the angle between the resultant and the horizontal. So this angle is what we are looking for. So whatever this angle gives us is going to be our direction. So to get this one, we can just say our formula using sine rule, which is A over sine A equals to B over sine B. That's going to be our formula. So what is our A? A is the side, while sine A is sine of angle. So if this one is our A, this one is going to be our angle A. If this is our B, this is going to be our angle B. So in doing that, we now say A, just say 3 over sine alpha that we are looking for equals to B. This is our B, which is the resultant. And we have gotten our resultant to be 6.08 over sine B. And what is our sine B? Our B is 120 degree. So let's cross multiply and find find alpha. So in other words, we can just say sine alpha here is going to be, if I cross multiply, it's going to be 3 sine 120 divided by 6.08. So what's going to be our sine alpha? So our sine alpha is going to be, so our sine alpha is going to be 0.4273, approximate it to 4 decimal places like that. So what is now going to be our alpha, which is our direction? Our alpha is now going to be the sine inverse of 0.4273. So what is the sine inverse of 0.4273? So it's approximately 20, let me just say it's approximately 25.3 degree. So in this case, if two vectors are acting at 3 Newton and 4 Newton acting at 60 degrees to each other, then our resultant is going to be 6.0828 Newton, while our direction is going to be 25 degree. So let's look at the next. In the next class, we'll be looking at the next case. That is in case whereby this angle, now in this case, this angle is 60 degree, but we have an angle that is greater than 90 degrees. So in next class, we'll look at those other cases, and then we'll look at how to resolve vectors that is more than 2. In this case, we are looking at just 2 vectors. So when we now have more than 2 vectors combined together, then how do we resolve those vectors? So I believe you enjoyed this class. Make sure you go over this classes so as to get a better understanding of it, and you can also drop your question in the comment section, which I will attend to if you do that. So kindly like this video, share this video, and make sure you subscribe to this YouTube channel. Thank you, and God bless you.